Welcome everybody to our next video talk of the spring semester. We are very pleased to have Joshua Gans here, who I don't think needs too much introduction. I'm assuming everybody here is pretty familiar with his work. Uh, does all things digital and then some, and always ahead of the curve in terms of sort of topics that people are interested in. Um, he's going to speak on how to train your AI when humans matter. And just as a reminder for those of you who have not been to the seminar before or don't remember, the way we proceed is the speaker talks for 45 minutes, largely uninterrupted. If you have clarifying questions, you can put them in the chat. And then at the end, for the last 15 minutes or so, we'll open things up for Q&A. With that, let me turn things over to Joshua.
Great. Thank you very much. Thanks for inviting me to present today. I've been doing a lot of work. I'm thinking about AI adoption. That's basically what I've been doing for the past decade or so. And this paper is a paper that my colleague Kevin Bryan and I have been working on for some time. Um, Basically trying to understand some of the broader economic choices that may be made by people who are actually training AI models. You might think that there is not much economics to that, but actually that's going to be our point, is actually there probably isn't much economics going on with regard to that in terms of the thought of training these things. But actually, when you think about what AI is used for and the fact that it is used by people, and people have not only their actions of using an AI, but also how they use it, that actually feeds back into some of the choices you'd make and some of the trade-offs you'd make in training your AI. And there tend to be things that the computer scientists don't think about. And so I'm not 100% sure whether the audience for this paper is the audience that is currently here or the audience of computer scientists that isn't here, but at least we can sort of agree on sort of what the message should be to them from this. So the title of this paper is still we've jumped around with the title. This is where we landed last week. We haven't yet produced the paper, but here's where the title is, which is inspired by, of course, the children's book How to Train Your Dragon, um, which I don't know if it's going to stick. But the thing that motivated us, you see all the time these benchmarks for artificial intelligence. Um, they're getting X% accurate or good at something. With the general desire, suggestion that if you can get to 95%, that's great, or something like that. That sounds like a good number. And so there's a lot of discussion about the 95% accuracy and things like that. But when you just think about things such as, for instance, how we'd handle a self-driving car, we kind of know that this sort of 95% rule is a little bit misleading. Um, for instance, if you have a self-driving car, a Waymo or something like that, um, it's gonna be it could be 95%, it could be 99% correct in terms of doing what you'd expect it to do in given situations. But when it fails, it doesn't tell you when it's gonna fail. It doesn't know. It's gonna just fail. Um, we've had automated driving things before. We've had cruise control for decades. And cruise control, as you know, works very well when you're driving at a constant speed for a long period of time, that is on a highway that isn't crowded. But you would never use it in the city because the choice of whatever speed you're going at is unlikely to be the speed you want to go at for the simple reason that often you want to go at zero. So that's a but it can do a very good job on the highways for some good period of time. Um, and then of course we can have people drive, and people are kind of like able to adjust all over the place. And but they've got to work. That's the cost of it. And so if you just sort of straight out looked at which one is accurate over all sort of instances, you'd get like the autopilot being accurate some 90 plus 95% plus time period of time, the human driver accurate maybe a bit more, 99% time in terms of what the human wants to happen, which is different than safety. And with cruise control, if you let that run, it'd be accurate like half the time or something like that. It's terrible accuracy. But actually, we know that that is a misleading thing because it has been, people do use it when they're able to sort of select when the appropriate thing is. In other words, there's a human in the loop, and that's going to matter for sort of what we're trying to produce. This sort of came up Kevin and I have a startup called All Day TA, which could revolutionize your dealings with students if you haven't had a chance to try it already. But it's an AI teaching assistant. And the goal there was to be able to produce something that could help to students that each individual professor would regard as more reliable than ChatGPT. And so ChatGPT, you can give it a question, such as this one. How many chucks would a woodchuck chuck if a woodchuck would? And it will give you an answer, regardless of, the merits of the questions, the relevance of the questions, or whether there actually exists an answer that is appropriate. Whereas if you gave that same thing into any course in all day TA, it would say, I don't know. I don't have an answer to that question. It seems like something different. Maybe you should talk to the professor about why this doesn't seem to be covered in the materials. Okay. So what's different between these two things is ChatGPT is what is called in the computer science literature as high coverage. It serves up a prediction, almost 100% of the time. Uh, All day TA is lower coverage. It's not going to give you an answer to things that it deems irrelevant. So it's got a rule behind it, and things that are relevant are things that it can't answer from the material that the professor has trained it on. So you see that with the coverage, actually, there's an interesting trade-off in these things. ChatGPT has higher coverage, so you'll get an answer more. That's something people do value, having an answer more, but it'll be at the margin, or maybe on average, will be a lower quality answer. All day TA, higher quality answer, less often. So it's almost demand curve like in its trade-off. So what do we do? So we have this model where humans, they're perhaps heterogeneous. They can get a costly prediction from an AI, and they can try to, if they want to verify that prediction at a cost, and then they can take an action. The developers who are training the AI choose the AI properties from a frontier that broadly is this accuracy coverage trade-off. And they're supposed to do it if they were being economically appropriate, maximizing value, understanding how the humans will use it. And how you train the AI differs depending on what you expect the humans to be doing. We can then characterize when the humans actually adopt AI at all, and also when they'll do it autonomously. That is, not engaging in verification, just accepting the answer as is. And this sort of is going to relate to broader questions of the economic value of AI and also how competitive environments and other settings affect all of this. So this is in part, is part economics, part framework. So what do we find? We find in general that high accuracy is often insufficient for autonomous AI use. This is the thing people are striving for, but uh, 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 you know, unless you could get to 100%, people won't adopt it under certain reasonable conditions. When verification, human checking or other checking is expensive and the errors are costly, you may not adopt AI at all. regardless of how accurate it is. And interestingly, optimal AI use, which is something we're exploring a bit more of, is discontinuous in these human decision parameters. In other words, when you look at graphs on how AI will be demanded, there's sort of like gaps. There's interesting gaps in the consumer space, which are interesting. Finally, we can sort of characterize the optimal training problem, using familiar tangency conditions and that. And we show that it just varies wildly depending on the economic environment. In other words, to train an AI without thinking about how the context of in which people are using it for is is likely to be an insane idea. Yet, it's currently the biggest investment uh, since the railroads being done with that based on not doing that. So that's interesting. So we extend the literature, as I said, there's a past literature on AI benchmarks, marks the criticism which is starting to be addressed is that they focus on standalone accuracy. How accurate are they, regardless of what a person is intending to do with it? Um, there's a literature, of course, that I've been involved in with AI has been lowering prediction costs, but only prediction costs, and there are other aspects of decision making that come into it. There's a literature on human AI collaboration, notably in sort of medical settings have been particular. And then there are also productivity effects from AI adoption that sort of talks to this. But again, that's sort of like trying to find broad measures of environment rather than very specific ones, which I think can matter here. Um, so our framework's going to be explicitly decision theoretic. It's going to have verification costs, going to have a veri cost, just like we like them. They can be asymmetric. The optimal decision rule will be derived, and then we'll do some applications. Okay, so what's that decision environment? Decision environment's characterized in our model by four parameters. First is the value of a correct decision, H. So you imagine people are choosing an action on the 0, 1 continuum to match a state that also exists on the 0, 1 continuum. In other words, if you're just randomly guessing, your probability is zero of getting the correct state. Um, the correct action, if you do get it, gives you a payoff of h greater than zero. The incorrect action could be heterogeneous for distribution of different errors that occur, but the average error is L bar, and that can be really, really negative. Um, if you choose not to bother making a decision at all, which of course you can always do, you get a payoff of zero. And you could do this the old-fashioned way, just work very hard at a cost of CS, and study hard and learn the state. You could do that perfectly. It's a cost of CS. The other thing you could do is you could get a prediction from the AI, and I'll describe that in a second, and you could engage in some cost to verify that the prediction is correct. That's less costly than trying to learn the state because you've been served up here's what I think it is, and then you can just check is this right or not, and it's a little a less costly, it's a less costly action. The AI model itself is governed by three parameters, a cost of running it, and also Q and P. Q is coverage, that is the probability that the model produces a recommendation at all. P is the probability that conditional on a recommendation being done, is it correct or not? So it's a conditional correctness. And the query cost is C per query. The overall accuracy, as they define it in the computer science literature, is equal to the coverage times the conditional correctness. So it's the overall probability that the model gives a correct answer. And so it's not conditional on being an answer at all. Um, there's some key assumptions that there's no output specific information about correctness. That seems pretty reasonable in this context, but we make it an assumption in the paper. Okay, so what's the training problem? The training problem, so that's the value side of things. The training problem is that you have to, given the model class and given the economic environment that I've just defined, you want to choose your probability, conditional probability, and also your accuracy, which is probability times coverage, from a frontier. And that frontier is AQ. And AQ looks like this in accuracy and coverage space. It is a concave function, increasing and concave function of coverage. That is, as you increase coverage, as you force the AI to generate an answer, the uh, accuracy of the AI price, not price, P times A, um, falls or increases at a diminished rate. And you can imagine the reason why is that, in effect, that you can rank answers in terms of their confidence. One thing is as you force it to do more coverage, it's giving less confident answers. So on average, the quality of the answers is not going to rise by as much. Okay, the marginal quality could be low. Um, so that's the thing that this could be derived from micro foundations. The computer scientists did that 50 years ago. I'm not going to go through that now because we like a concave increasing function to describe things. That seems very production function worthy, so it doesn't feel controversial to me. Um, what about verification itself? What does that mean? So verification in our model is going to be you you get a prediction, uh, you expend this cost CV, and then you learn whether the prediction is correct or not. And if it's correct, you know it's correct with 100%. If it's not correct, you're back to square one. You don't know anything. So what can that be? I mean, part of that could be like what I like to call spidey sense, which is like your experience and cues of thinking of, is this the right answer? You know, like this does this make sense to me? Um, but it could come from all sorts of internal things. The other thing that could become from verification is that you run explicit checks or auditing. You check another way. With respect to code, does it run and does it produce the output you expect? This checking or auditing procedure could, of course, be AI assisted as well. There's nothing stopping that. We're not going to sort of like delve into that here, but that's another thing. A final thing is like peer review. I've been doing a lot of using AI to help me write theory papers, and one thing I've noticed is that peer review, somebody else taking a look at the paper, is very useful. Funny that. So these aren't new things, but they all have in common that they require someone to say, "Hey, I'm going to check this out." So they have a cost to them. So they're very much they're not autonomous. If you're expecting you're going to get results and you're expecting to verify them, you are expecting to have a person still involved in the overall decision-making process in a way. And above and beyond their other involvement, such as you get a prediction of the weather and you're deciding, should I take an umbrella or not? You're not going back and saying, well, I don't think the weather service is correct. Instead, you're saying, oh, am I going to be outdoors today or not? Other context. Verification is literally, do I believe what this thing is telling me? So the timeline for the model is very simple. If you choose to, you do an AI query. If it does not give you an answer, you can go to the baseline. You can just solve it out yourself or not do anything. If it predicts, which happens with probability Q, you get a prediction. You can choose to trust that prediction. You can act on it without checking. If you act on it without checking, then if it's accurate, um, you'll be able to earn a high, an H rather than an L. If it's on the other hand, if your expected probability of being able to do that is if it just does if it returns an answer at all. If it doesn't, then you're in trouble. If you predict and you want to verify, then your accuracy is now a little bit different. Is like you are going to because you're going to verify, you can still get H, but you're sort of insured. The worst you can do is if you're only going to act if it's confirmed from the verification, the worst you can do is the baseline. So in other words, by verifying, you cut your downside risk. You cut your downside risk, but obviously at a cost that you have to verify whenever a prediction actually emerges for you. So as you increase the quantity, the coverage, you are going to spend more in verification costs as opposed to just taking the gamble that the prediction is right. Um, okay, so this has computer scientists coasted towards this problem, um, not with the verification bit, but with the trust bit. And so there's this paper by Chow back in 1970 that we dug up, and it actually characterized in a sort of broadly economic way this problem of selective classification. That is, when should a model that is giving a prediction, they didn't have AI back then, but it was they were thinking statistically, abstain rather than risk an incorrect prediction. And the assumption was that people were going to take an action based on that prediction. They were going to trust the model if it gave a prediction. And so the issue is sort of like, is it a good idea to not know? Say, I don't know. And the answer was, you would think about that very carefully if the error that you get, the loss from an error, is much less than the baseline. In that case, you would abstain rather than risk a prediction if the probability of being correct was less than this ratio of the baseline to the error to the hopeful outcome to the error. Um, and you would choose to abstain in that situation if the model is insufficiently accurate, obviously. Um, but what that would also give you is the ability to think about this trade-off. Specifically, actually, let me just jump forward one bit. Well, if you're going to trust, um, um, in our conception, what you would do is you would think about the expected probability that you'd receive from that, and then see what you can get given the technical constraints of the accuracy frontier. Let me show you that in a graph, actually. I'm going to just flip it forward because it's a bit easier. If you look at the graph on the left-hand side here, you can see the AQ frontier, and then what we've done is shown a tangency of that trust line of an ISO payoff, and the ISO payoffs are based on the expected return from trust. And obviously, you want to choose a coverage such that the tangency of that frontier is equal to the slope of the line. And the slope of that line is exactly this ratio that was right here, derived by Chow. So that pops right out. I'm sorry. So that means that basically you can get some interesting things in this environment. If you hold accuracy fixed, a higher P or lower Q strictly increases value whenever B is greater than L. So accuracy tends to treat errors and rejections symmetrically, but we wouldn't do that as an economist. We would treat them asymmetrically because errors in this model are costlier than rejections. And so you can have a model with the same accuracy, say, of 80%. Model A generates that accuracy from serving up an answer all the time at 80% correctness. Model B serves up the answer 80% of the time, but at 100% correctness, conditional probability. And so model B is clearly strictly better because it knows when it doesn't know. And so you choose that model rather than the fully more accurate model because you have these asymmetric errors. Um, I say that again because remember, all these companies are trying for Model A, trying to produce Model A, and they're serving it up to everybody regardless of any knowledge about what the consequences are. The other thing is, so what we also add to this, of course, is verification. And you want to verify if the verification costs are low enough relative to the baseline error that you might get from trusting. Okay. And so you would choose whichever regime you should trust or verify based on these different costs, and you would adopt if the max of these things is greater than not adopting. So you can actually have situations where you don't adopt with high accuracy. If you've got a situation where the cost of verification is high and L is very negative, even when your accuracy is very high, you will choose not to adopt. Because accuracy, I mean, if it's 100% accuracy, obviously that's no problem. But if you've got a high accuracy, but you've got these consequences that are very grave, high stakes, and also you don't can't engage easily in the verification ex post for whatever reason, then it's better off not adopting at all. Um, okay, so uh, in, as I mentioned before, the optimal rule is to offer a prediction, offer a coverage if this equation is satisfied. That's from Chow's work. You can do some simple comparative statics. If the returns are very negative, the errors are very negative, you choose to set tau would be equal to 1, and you'd hardly ever offer a prediction. You'd have to be dead certain to offer a prediction in that situation. If you only have mild errors that offering a prediction is no more risky than the baseline, you'd almost never reject. You'd always offer predictions. As you get your better outside option, interestingly enough, you would actually try to make your AI more selective. Because remember that B is entering both into something that occurs is the B is the margin on which you decide whether to adopt or just trust in the Chow model. So it impacts that slope. Um, so in this paper, so Chow basically looks between, am I going to trust this prediction or the baseline, and it, comes up with a coverage and conditional correctness. In our paper, we add the verify line, and that's like pure, so long as the cost is going to engage, it's not too high. It's a pure extra option. So it's always going to be taken by some range of decision makers. And in fact, you can basically show, and this is not too surprising, when you've got very low verification costs, the verify area can be quite large. Almost as if anytime you're getting a prediction, you're verifying it. Um, when you've got a very high verification cost, we're back in the Chow world, and so you're thinking between trust and a baseline as your two options. And if you are in the if you're in a situation where you've got a very high base to error ratio or very low base to error ratio, then you get a situation which you hardly ever trust. Even with very high degree of accuracy, you would hardly ever trust. So that pops out of the economics of it, which is kind of neat. So the optimal training is basically going to be regime dependent. If I expect to trust, if I was designing a model where I expected to trust, which of course has to be in equilibrium, but let's just go through the exercise, then I would set the tangency of the accuracy frontier equal to the Chow ratio. On the other hand, if I was expecting people to verify, that is, if CV was low enough to engage that, I'd set that tangency equal to the verify ratio, which is a different thing. And it's a different thing both on the denominator and the numerator, but it tends to be steeper. And so so it tends to be flatter. So if you look here on the right-hand side, it is an example where you both have a tangency for both the trust and the verify lines. And you'll notice because the verify line is the slope is not as steep, you'll always choose more coverage under verify than you would under trust. And this is not surprising because what verification allows you to do is mitigate the downside risk associated with trust. And if you can mitigate that downside risk, you're willing to accept the risk of less accurate predictions because you're covered from the downside risk of it. So you want more predictions, less accurate if you're verifying. If you're only going to trust, on the other hand, you want fewer predictions coming to you because you want them to be on average much better. Um, but of course, the uh, coverage itself delineates whether you will trust or verify. So we have to make sure to find the global optimum, or to even know if there's a too local optimum, that the demarcation point between trust and verify in terms of coverage. So there's more coverage I want to verify, less coverage I want to trust. The two optimums lie outside of that. If they don't lie outside of that, one of them is going to be a corner. So it's a little bit messier to deal with. But notice one important thing. Here's a diagram here where both are, possible. As you raise the cost of verification, okay, we're going to change the slope of the verified tangency. We're going to reduce coverage, is what's going to happen. But also we're going to change that dividing line between them. What's very interesting is that you can get this discontinuity as you raise V. All of a sudden, you switch to trust, and you jump in terms of the training. In other words, the correspondence of Q star globally is discontinuous in CV. As CV rises to some threshold, you will dramatically change the coverage you would choose. And that happens no matter what sort of parameters you do. There's no easy smoothing that out, which is also interesting, and that has consequences I'll try and mention in a bit for pricing actually. Um, the other thing that comes from this model, and I apologize for not being able to show this in a clean way. I've been trying to practice with different ways, but I haven't found one yet. But you have a diverse population. And so different people would want the models to be trained in different ways. If you're a cautious user, you don't want it to return answers very much. If you're a reckless user, you always want an answer, and then some average in between. And so what that means is there's no way of ranking these models in the usual Blackwell sense because all the individuals are very different. Depending on the situation, if the errors are mild, you might want a model with high coverage. If the errors are costly, you want a model with low coverage. But what's worse than that is like the sort of like welfare implications are as you move away from the average, the welfare reductions are increasing and quadratic in the model here. So, you get these sort of huge downsides at the tails. All very nice if the population's normally distributed around something with not too much of a variance, but if you have it very wildly uncertain, this could be a real problem. Um, and this impacts. How do I get back to Blackwell ordering? Well, the issue is that in the models we serve up, we're not actually giving people. We're giving people the prediction, and it's a pooled prediction based on how they've trained the model. And so, and essentially the developer's choosing that for the average. So we can't Blackwell rank those. The way we could back that out would be if we produced alongside the prediction some sort of, say, confidence score, then people are able to take that confidence score and use it in their decision making. And so if a model can actually report those calibrated posterior series. And by the way, that's a big if. It's really, really that nobody's really quite worked out how to do that. To do that, calibrated to what is the whole issue. And they can be observed for free, then that would be great. So formally, so you instead of trying to balance your selectivity and coverage, what you're doing is you report the probability is correct with some probability, the prediction is correct with some probability, and then the agents can decide what to do. And this is a deeper problem than that. I'll just advertise another paper. I've written another paper about this, about how we should take into account preferences. Hal Varian for many years was telling us we should take into account preferences by putting it in the loss function when we train these AI models. But actually, if you work it out, um, the problem with that is it changes the range of predictions that models can give. We're doing a lot of things that are reducing the range that can be reported due to preference issues. That's a terrible way to do things. It's very, very costly. It would be much better if we had people apply their own preferences and expected them to do so, rather than crimp our training by trying to take the preferences into account during it. Anyway, that's a little aside. So we have this sort of situation where we've got one of the things we've got in the world is we've got one size fits all models being produced at massive scale. One size fits all, one model for six, eight, how many billions of people? And they're choosing and leave aside any I'm trying to maximize profits distortions that are coming from this, or market power or something like that. That already is a very challenging thing, and the more different people are, the more problems that you've got. Let alone that we're training that over just people's different preferences, but also their different ability to use verification. As I said, verification can come from experience and stuff like that. It is very different when you present and train a model for someone who's going to be used, who's experienced and is going to verify it, versus someone who's not, let alone the same model covering both of those cases. That's unlikely to be optimal. Now, it's not that surprising. When individual preferences are individual, that we might have some trouble satisfying them without a personalized product. But just thinking about the scale upon which these are currently being served to us, you got to wonder whether there might be a better way. One of the things that occurs is if you sort of take some heterogeneity both in the cost of verification and the downside risk of errors, you can get these sort of like you've got a trust and verify line between which is the black line there. And you've also got people adopting if they're paying a price to adopt. The trust buyers being the people with low L bar, and the verified buyers being people with low CV. Um, and you get this sort of interesting wedge occurring in the middle that I've only just started to explore, which sort of like, in other words, the same price is producing this sort of gap in the market, which stuffs up all our thinking about things at the margin. In particular, the thing that I'm interested in is where the current LLMs appear to have very high coverage, Q equal to 1, and they give you no help whatsoever to help you verify things. And so the question is, what conditions support that outcome? Why would a LLM, presumably with some market power, well, that's presumably, to make those sorts of choices? And so that's sort of where this is going to go a little bit next. Obviously, we can do the whole Spence thing as well if we want to, and we get distortions from the monopoly buyer there. Nothing too exciting that way. So in the final 5 minutes I've got, I'm going to run through very quickly a whole lot of applications that you can use the baseline model to sort of test and do. One is, first of all, is adversarial manipulation. This is a hot topic, very hot topic today, by the way, because Claude have refused to release a model because they're worried about this. Imagine you have a situation where you can take an answer and insert something incorrect into it. That's what an adversary will do. The output is different. The missiles aren't coming. It's not going to rain tomorrow, whatever it's going to be. So, some sort of lie with some probability. Then that is going to affect both the trust and the verify slopes. And it's also going to affect how the optimal coverage. Obviously, since you've sort of crimped the model somewhat, you basically shifted that frontier down. You want to do lower optimal coverage as a result of that. But relatively, the verify region would increase relative to the trust. Again, that's actually quite intuitive. If you don't trust the model even more, you're going to, want to verify more and trust it less. And but the interesting thing is you can sort of put in the sort of basic story straight into the model. You could also have the verification currently is perfect. You could have imperfect verification that's going to do exactly what you expect. It's going to shift the agents away from verification towards trust and abstain, and it's going to change your coverage accordingly because of that. Um, you could have situations where the verification task is you've got a committee and and so the community is getting a prediction from the AI, but you want to have some verification, and it only requires one of you in the committee to verify, but there's private costs. Well, that's going to reduce the verification mechanism right there. So you might want to have lower coverage in your training as a result of that. Unless, of course, you could assign responsibility to the person to do the verification, in which case you can resolve that. But so we can have some free riding problems. We can have some O-ring issues. This is something that Avi Goldfarb and I have been looking at in another context, but where you have a number of tasks that are all related and their quality is all related to each other very tightly. In that situation, um, uh, if you have a single bad step that destroys all of the value, you really, really want to verify more for moderate task lengths. If you have a very complicated task, don't want to adopt AI at all. If you have a very simple set of tasks, you might trust, but for moderate ones, you would verify. So again, the idea is like, so for moderately complicated tasks, you want to have a human in the loop. Um, we could also look at payoff externalities. These can be where the good outcome is or decreasing in the number of other people in your game that have a correct or not. It's decreasing when there's sort of competition. You like to be the only one who's right. In that situation, the marginal value of correctness goes down, and so you want to favor less coverage. In complementarities, where you're trying to, get more people to be successful, you want to actually favor broader coverage because it changes the ISO payoff curve start to flat and then it goes towards broader coverage. So there could be applications where you could be more specific about these things in order to derive what we should be doing, what sort of AI we should be serving up to people in different contexts when there are payoff externalities. Um, oh, this is just a summary slide of pretty much I just said. We do a couple of other things, look at limited liability and some other stuff which could have regulatory issues, which would be interesting as well. Um, just to close it out here, the implications of all this for benchmarking and training, which is a whole industry. The current practice is to report headline accuracy. We would not want you to do that. You should report both accuracy and the degree of coverage. Obviously, if the coverage is one, that's not an issue, but we would like to, if people start choosing that, it would be a useful point. Um, Current practice is also to have a single deployed operating point, but we would like to think about, we think there's a return to showing some calibrated uncertainty to help people understand confidence. Um, People are currently trying to maximize accuracy, forcing Q equal to one. That's clearly not a good thing to do. It's not a good thing to do whether you got individual specific information or you're pooling across them. So long as they're different, you're not going to want a coverage equal to one. They treat all users as identical. That's not great. You have to trade off the scale benefits or technical benefits of that versus tailoring. And they currently evaluate models in isolation, but we've really got to move to workflow evaluation because people are engaging in these verification tasks, and they've also got chains of tasks and all sorts of other things that are surely relevant. And the point of this paper is to say you would change how you train this model when you understand those things. You'd change. Final bit of advertising, obviously startup, and I recently wrote a book. I mean, it was published last year. It was written in 2024. I think the first line is this book is out of date. But nonetheless, up until that point, it deals with a lot of micro issues to do with AI. Okay, thanks.
Great. Well, thank you. That was awesome. So we typically just have people kind of jump in with questions. So if you have a question, if you want to maybe like unmute yourself and jump in. Yeah, raising hand probably good too.
I have a question.
Yep.
Can I? This is great stuff, Josh. I really enjoyed it. I mean, with my IO hat on, I cannot not talk about the whole issue of free entry distortions in the market. In other words, you're stating a fact that the systems that we have are perhaps too much geared towards the average person, but they're not specialized enough. Maybe you already wrote this paper, but is this a case of the tyranny of the majority, to use Joel Waldfogel's terminology, that the market equilibrium is itself distorted towards the generalist and does not cater to the more niche kind of part of the market?
It it's really hard to tell at the moment. I think you know, I'd call whatever you're trying to make observations on what is current is trying to make observations which is surely disequilibrium. We have so many
Right.
bottlenecks and constraints everywhere, so it's a little bit tricky. But at the same time, I'm waffling between my IO hat, which is positively what's going on in the market, how can it be explained by the model, and my strategy hat, which is what are these people insane? So there's a bit of that going on, and I think we definitely don't understand everything that's happening. The one thing that I'm interested in, I was focusing on, I was hoping to get a result on. I've got a conjecture, is that if we compare monopoly provision of these things, the sort of one size fits all model, but monopoly provision versus competitive provision of the same thing. Um, and we think about a situation where at some sort of cost, the providers can do things to reduce your costs of verification, make it easier for the user to check the results.
Right.
I believe that there is insufficient my conjecture, which I have half proven, is there's insufficient incentive for a monopolist provider compared to a competitive provider to provide that verification. And the reason is that the providers in the business of providing a model that the consumers can just use. I mean, if you have to verify it, it's like, oh, I have to do another thing. And so, normally we're like, okay, if you want to do another thing, well, let's make it easy for you to do so if that increases adoption. And that effect is there. But there's this counter effect is that um, it's forcing fewer people to just engage in the trust of the model, which is sort of reducing the value of that. And so I think that's where the revenue hits. And it's related to that wedge that I pointed out earlier, this thing that doesn't seem to go away regarding the sort of optimal model from the demand side. So I need to work that. We need to work that out before this paper appears. We'll have either worked it out or not. Yeah.
Right. I have another question, but maybe there are other people who have questions now. But if
Keep you on
not, I
the.
mean, one very practical question, you probably know this. Why don't these engines or these systems have a knob that where I, as a user, can regulate coverage?
So they do have a knob. They don't put it in the chat GPT type thing or any of those things. But if you use it through the API, you can
Uh-huh.
twist a lot of these things
Okay.
to do that, which is of course what we're relying on in all day TA. That we're twisting that knob. So you can do it a bit. It's still a bit imperfect because remember, there's an issue of what does it mean not to know? So,
Yeah.
so they, you could have you have to give it a confidence score, which is its own metric, and let it go up and down. Now, if that confidence score is correct, then we can do everything we just said here. But if
Right.
that confidence score is so, there's different ways of thinking about confidence, which I think is a research topic, by the way, to work on, which is like, you know, if you look at a weather app and you see that it basically says there's a 10% chance of rain in a given period, right? So you say, okay, that's a coverage for that. That's the prediction, that's the confidence of it going on there. But at the same time, if you think about a richer space, what does it mean to be confident in prediction? We're thinking about, oh, I can tell you whether it's going to rain or not. That's a confidence. But if I'm kind of give a forecast, is it going to rain or is it going to be sleet or nothing? And then it may be that there's a high probability that it's both rain and sleet. So my confidence of rain and my confidence of sleet are very low, but they're not really low. The set of them is actually quite high. And so often it's the case that I want to know about the set versus other things.
Right.
How do you even train an AI to work out what it is I'm interested in? Or even the one I've been playing with is knowing when to ask her, hey, are you really interested in rain per se or something else? Like,
Right.
how do you engage it? That's a whole exercise that no one's even developing models
Yeah.
to
I mean,
really
it's sort
help.
of like the feel like kind of thing. Feel like is an instance where I'm
Feels
getting
like
a
it.
sort of
Who is
composite.
that person? Feels like to who?
Exactly. I sometimes complain about that. Exactly. What do you mean
No,
by
no, there's some person that the weather service has put into a room and say, how does that feel to you?
anyway, I see there's someone with a question in the chat, so I'm going to shut up.
Yeah.
So very
Oh,
interesting
sorry, sorry.
stuff.
Someone can speak. How to think about the dynamic pattern here, especially output of verification work and serve as a public good that helps next. Oh, geez, I don't know. I mean, I think that that's recursive self-learning. Recursive learning. There's recursive learning with human feedback. There's recursive self-learning and other things like that. That is a whole frontier, which, there's research going on for automated versions of that. But what about with people? If you've ever turned on memory on these on ChatGPT, sometimes you're doing research at one level, and then and another time you're trying to work out what's a good light how to change a light bulb, and of course they sometimes can conflate with one another. So how to actually transfer? It's like a massive problem. You very much get you very much see how we've pushed so far on one dimension of intelligence and not on other parts when you think about these things.
Mhm. So I had a quick question. In terms of characterizing what, you know, the sort of general LLM companies are doing. So I'm thinking of ChatGPT. ChatGPT doesn't, I'm not so sure if the way you're characterizing what they do is exactly right. They offer multiple models, like you can pay, so freemium or not. And Tommy and I work together. Tommy gets the good stuff. I'm cheap. I don't get the good stuff. And it also limits what I get because I get X number of queries and I'm done. So I mean, they're
All
probably
right.
doing this for very different reasons, but
Right.
they're doing some aspects of, I guess, some. Well, anyway, I don't know if it's possible to sort of look more at that kind of policy. And
Well, that's a different sort of thing. There's a very interesting thing regarding the LLM providers and how they've chosen to rate limit you, right? So you can limit the number of queries. You can also limit the level of the model. That's different from anything we've been talking about regarding coverage. This is like given a model. will it give you an answer or not? And invariably, it's going to give you an answer because that's the way they've done it, which is the variable we are. We would prefer the AIs to come up with, I'm not really sure here more often than they do, or to provide that information somehow. And what's worse is they're not telling you when you use the lower models versus the thinking model, oh, I wouldn't use this model for that. I don't know if anyone's ever seen that. I've never ever seen a cheaper model say, you really should use the better model. Can I introduce you I don't even know why. Can I introduce you to a better plan?
It also it does do that sometimes for me. Like I'll use it
Okay.
for coding, and it'll be like, yeah, don't be so cheap. Do the better model.
Well, no, I mean, it will if it runs out of token. Is it doing it because it thinks it's going to do a shitty job, though?
It's even like before, like, well, I can't
Okay.
figure out whether it's I'm getting close to the end or not.
Yeah.
One, just as an aside, the thing that I also find puzzling is it doesn't say you're about to run out. It just stops.
Yeah, no, no,
Uh,
that's another thing. Well, some of the different ones give you different information on that. I mean, obviously Claude had this sort of millennial characteristic. You'd be working in the morning and says, that's fine. I'm done now. Come back after lunch. I'm on a break." Whereas like OpenAI would shove you to a lower model, or Google would give you some, like they've all got different plans, which is an interesting question as to why they do in that regard. Why that's one thing that you would think that would there'd be an optimal solution to. All right, I think I've
Anybody else want to jump in with comments or questions? We got a couple minutes, but we're also pretty close to the to time. Going once, twice.
Yeah, just
Oh,
hi Josh. Thanks. Very very interesting stuff. Just a question about so your point is about yeah all the main players are choosing models with very large very high coverage, but you've got also a lot of specialized players. No, so
yes.
how much of it do you have? I know little, but all ATA seems to be like one example where you choose a.
Yeah. Look, there are a few ones out there. It seems to relative to what the model is sort of saying to us, there doesn't seem to be a lot of that. I mean, there are some specialized things out there that do different things. And obviously this hit us hard because we knew we had this problem right away. In other words, we knew that it was better to have a don't know than an incorrect answer for students. So that hit us 3 years ago when we started this. So hence the putting it into a model and thinking about it. I suspect there are other situations. I mean, one of the issues that we have is we're not 100% sure of when the costs are really big for that. As I said, with teaching, it was like easy to understand why this was a big issue. I suspect that's definitely the case in medical stuff. So I don't know. I haven't had a chance because I'm in Canada to try the ChatGPT Health or whatever these things are that they're trying to do there. But one imagines that that's a whole set of stuff that would have to be calibrated this way. I wonder what's being done in the sort of use of a psychologist or counseling programs and stuff like that. You'd also want those to be a little bit differential, but that's an interesting case as well. So as I said, it's tricky. I mean, I suspect the answer is, none of the above is that these models will work better if they start working with you rather than trying to satisfy you. And by satisfy it means like I'm happy with this answer. I don't have to do anything else. I think that's the way these have to move. But that's like we do a bit of that in all day TA. For instance, we have multiple choice questions, and when the students get a question incorrectly, we don't tell them the correct answer. They want it. They would like it, but we don't tell them. We say, well, why did you choose the answer you did? And then we tell them the correct answer and explain how it's different to whatever they were thinking. That is along those lines. But, that had to be massaged and crafted specifically for this use case. And that's not what these people are all on about. They're on about by next year replacing all work or something. Um, so they're on a different path. I just am skeptical about whether that will fly.
Okay, good. Well, we are now at time. So again, thank you, Joshua. That was great. And thank you everybody for sticking around and questions and comments. Just as a note for those of you who are around, our last video talk of the semester will actually be a little bit delayed. It won't be towards the middle or end of May. But anyway, hope to see everybody there. And yeah, that's it. Um, Joshua, real quick.